What really happens at the heart of a black hole? Join us on a mind-bending journey as we dive into singularity, the mysterious point where all our rules of physics seem to break down. Imagine a place where gravity becomes so strong it crushes even atoms themselves, a place where time itself grinds to a halt. We're talking about a point of infinite density, a cosmic abyss that challenges our very understanding of the universe. Ever wondered why time slows down and eventually stops in this strange realm? In this video, we'll unravel the science behind why time doesn't exist in a singularity and explore the top 5 incredible facts about singularities that will leave you in awe.
Okay, picture this. You're falling into a black hole. Don't worry, it's just a thought experiment. As you descend, gravity gets stronger and stronger. That's because you're getting closer and closer to the black hole's center, where all its mass is concentrated. At the very heart of a black hole lies the singularity. Now, we call it a singularity, but it's not some tiny speck you could see with a microscope. It's a point, a location in space where gravity becomes infinitely strong. Think about what infinite really means. It's not just a big number, it's bigger than any number you can imagine. And when we're talking about infinite gravity, we're talking about a force so powerful that it squeezes everything, and I mean everything, down into an infinitely small space. This means that at the singularity, all the stuff that makes up a black hole, whether it was originally a giant star or a nebula a million times bigger than our sun, gets crushed down into a point with zero volume. Zero volume and infinite density. It's enough to make your head spin. And it's here, at this point of infinite density, where our understanding of physics starts to break down. See, the rules of physics that we use to describe the universe, things like Einstein's theory of relativity, they work great for most things. But at the singularity, they just don't apply anymore. It's like trying to divide by 0 on your calculator. You get an error message. This breakdown happens because at the singularity, gravity becomes so intense that it distorts not just space, but time itself. And when you mess with space and time, you're messing with the very fabric of the universe. This is why singularities are such a mystery. They represent a point where our current understanding of the universe hits a wall. But they also offer a tantalizing glimpse into the potential for new physics, new laws of nature that we haven't even begun to imagine. So, buckle up, because as we journey deeper into the mysteries of black holes, we're going to encounter some truly mind-blowing concepts.
Let's talk about space-time. I know, it sounds like something straight out of Star Trek, but stick with me. Imagine the universe as a giant trampoline. This trampoline is space-time, the fabric of the cosmos. Now, when you put an object on a trampoline, it makes a dip, right? Well, in our cosmic trampoline analogy, massive objects like stars and planets are like bowling balls. They create dips or curves in the fabric of space-time. That's what we perceive as gravity, the curvature of space-time caused by massive objects. Now imagine a bowling ball so heavy it stretches the trampoline to its absolute limit. That's a black hole. It creates a gravitational well so deep that nothing, not even light, can escape its pull. But here's where things get really weird. At the singularity, at the very bottom of that gravitational well, space-time itself seems to curve infinitely. It's like the trampoline tearing apart at the center. This infinite curvature is where Einstein's theory of general relativity, as brilliant as it is, starts to show its limits. You see, general relativity is really good at explaining gravity on large scales, like the motion of planets and stars. But at the singularity, where gravity becomes extreme, the equations break down. It's like trying to fit a square peg into a round hole. The math just doesn't work. This breakdown tells us that we need a new theory, a theory that can handle the extreme conditions found at the singularity. This new theory would need to combine Einstein's theory of relativity, which explains gravity, with quantum mechanics, which explains the behavior of matter at the subatomic level. Finding this theory of everything is one of the biggest challenges in modern physics, and singularities, with their mind-bending physics, hold the key to unlocking this grand unification. So, the next time you think about black holes and singularities, remember that they're not just cosmic oddities. They're cosmic laboratories that could help us unlock the deepest secrets of the universe.
Einstein changed the way we see the universe. Before him, gravity was a mysterious force acting at a distance. Einstein showed us that gravity is the curvature of spacetime, but his theory couldn't explain black hole singularities. This is where quantum mechanics comes in. Studying these extremes might unlock the secrets of the universe.
Chapter 4. Time travel. It's the stuff of science fiction, right? But what if I told you that black holes might hold the key to unlocking the secrets of time itself? Now, I'm not talking about hopping into a DeLorean and going back to the future. I'm talking about a fundamental shift in our understanding of how time works. You see, in our everyday lives, we experience time as linear. It flows from the past to the present to the future, always moving forward. But Einstein's theory of relativity tells us that time is not absolute. It's relative. This means that time can actually speed up or slow down depending on how fast you're moving or how strong the gravitational field is around you. It's true. The faster you move, the slower time passes for you relative to someone who is stationary. And the stronger the gravity, the slower time passes. Now let's apply this to black holes. Black holes have incredibly strong gravity, especially at the singularity. So strong, in fact, that time literally slows down to a crawl. Imagine approaching the event horizon of a black hole. From your perspective, time would seem to be flowing normally. But from the perspective of someone watching you from a safe distance, you would appear to slow down, your movements becoming more and more sluggish. As you got closer and closer to the singularity, this effect would become more and more pronounced. Time would almost seem to stop altogether. And at the singularity itself, where gravity becomes infinite, well, that's where things get really strange. Because at the singularity, time as we know it ceases to exist. It's not just that clocks stop ticking, it's that the very concept of past, present, and future breaks down. Everything converges into a single point, a timeless eternity. Now, I know this is a lot to wrap your head around, but that's the beauty of science. It constantly challenges our assumptions and forces us to expand our understanding of the universe.
Chapter 5. We've talked a lot about black holes, as if they're all the same, but it turns out there's more than one kind of black hole. Some are stationary, like giant cosmic vacuum cleaners just sitting there, sucking in anything that gets too close. But others, well, they spin. And these spinning black holes, known as Kerr black holes, are even weirder and more mysterious than their non-spinning counterparts. Imagine a figure skater pulling their arms in as they spin. They spin faster and faster, right? Well, something similar happens with stars as they collapse into black holes. If the star was spinning before it collapsed, the black hole will spin too, and it can spin incredibly fast. Now, this spin changes everything. It's not just that the black hole is rotating. It's that the rotation actually drags space-time along with it, like a spinning ball dragging a tablecloth. This effect is called frame dragging, and it's one of the most mind-bending predictions of Einstein's theory of relativity. It means that near a spinning black hole, space itself is twisted and distorted. But here's the really cool part. Because of this frame-dragging effect, the singularity at the center of a Kerr black hole isn't a point anymore. It's a ring. And this ring singularity is where things get really interesting. You see, some physicists believe that it might be possible to travel through a spinning black hole without getting crushed at the singularity. Instead of being crushed, you might be able to pass through the ring singularity and emerge into a different region of space-time, perhaps even a different universe. Now, I know what you're thinking. Hold on, are you saying we could travel to other universes through black holes? And the answer is maybe. It's highly speculative, of course, and we're a long way from having the technology to test this theory. But the possibility is there. And it's just one more reason why black holes are some of the most fascinating and mysterious objects in the universe.
Thanks for joining us on this incredible journey into the heart of black holes. We've explored the mind-bending physics of singularities where gravity becomes infinite, time stands still, and the very fabric of space-time breaks down. We've delved into the mysteries of spinning black holes and the possibility of traveling to other universes. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more mind-bending science content. See you next time.